to be looking at diffraction of light and diffraction of sound for today's video. So this is basically all you need to know about diffraction of light. So first one is the cause, why diffraction of light happens. And second one, you need to know the definition for monochromatic light, because the effect of diffraction will be more obvious if you use a monochromatic light, basically. And then you need to know about two experiments, which is the pinhole experiment and also the single slit experiment. Okay, so let's look at what causes is and also the definition of the diffraction of light. So of course, the definition for diffraction is the spreading out of this light, right? And for light diffraction, it happens when light passes through a narrow opening, or also called slit, okay, for the single slit experiment. And for the pinhole experiment, the opening is the pinhole, the hole. Okay. Okay. So the pattern that you can see, or the effects of it, it will show a bright and also a dark fringes, call it. And if it's a pinhole experiment, we call it a dark and bright rings. So other than the word fringes, we also use the word bands sometimes. And these bands and also these rings or fringes, the center of it, or we call it central maxima, will have the most or the maximum intensity. So it will be the brightest. Okay. So now let's look at the definition for monochromatic light. So when we talked about monochromatic light, mono means one. So that means that light with only one color, one wavelength, or one frequency. So any of these three will be accepted as your definition. But usually we will say that light with one wavelength. So example will be lasers. Okay, so this picture here is how the band look like for a pinhole experiment. But sometimes it might not be this circular. Sometimes it may look like a little bit like a flower, so it will be like that on the side too. Okay. And this here is the central just now, so it's the brightest. For single slit, so this part here is the central maxima, so it's the brightest. Okay. So this is how the experiment is, okay, for the diffraction of light. So what you've got here is the slit. Okay, so that opening that I talked about just now. And in a lab setting, you can get this slit because it have to be like really small, less than 1 millimeter. So around 0.0 something millimeter. So that's very small, because if you look at this ruler, right? So I've colored it here. Okay, this small. Okay, this color here is 1 millimeter. So if it's for the different kind of diffraction gratings, I'll show you later, we'll have like a setting of 50 lines per millimeter or up to 500 lines per millimeter. And that means like if it's 50 lines per millimeter, that means that this size, this small size here, colored size, you have to cut it into 50 pieces. So that's how small the slit is, okay? So for 50 lines per millimeter gratings, that means that the slit size will be around 0.02 millimeter. So you cut this by 50. If it's 100 lines per millimeter, then it will be 0.01 millimeter. So you cut this by 100. And even smaller slit will be like 500 lines per millimeter. So that means you cut 1 millimeter to 500 lines. Then the size of your opening or your slit will be 0.002 millimeters. So very, very small, right? So for diffraction of lights, the experiment can be shown by using this diffraction gratings. This is 50 lines per millimeter. So that means this is a very wide slit, because for every 1 millimeter, it's like you cut them into 50 lines, right? And then I've got one here that is 300 lines per millimeter. So this one is like every 1 millimeter you cut it into 300 lines. So that means that it is very narrow. Okay, and then somewhere in the middle, this is 100 lines per millimeter. So now I'm going to show you how it looks like. So I'm going to start with the narrow slit first, which is 300 lines per millimeter. Okay, so like that. And now the medium one, which is 100 lines per millimeter. You see it on the board and it's getting closer together. And then a wide one, which is 50 lines per millimeter. So you can see that the lines are closer together. Okay, so when the light passes through the slit, through here, yeah, then this is the pattern that it shows. This is in terms of its brightness or in terms of its intensity. So here is the brightest, which is the central maxima. And here are some lights that you can see, some lights that you cannot see. So this, something that you call a tra here, okay, this will be the dark band. So this is where you see light, this is where you don't see it, don't see it, and so on, okay? So if we rotate this into this, then how you see it in the experiment will be like this. So this here is the central maxima, and this is the second band. And usually the other bands are not that visible if the size of your slit is not that small. Okay. Okay, so later on you will be learning about interference of wave. So that is when you have two waves undergo or passing through the same narrow slit as well. So it will look something like this, but we will discuss this further in the next topic, which is interference of wave. But basically, it is still the same as diffraction, only that you've got, if it's a diffraction, then this is your central maxima. But now you will have multiple dark and bright fringes inside one central maxima. And if you want to look at the picture of it, then it will look something like this. So for a single slit, then it will look like this, like we've seen before. For double slit, you can see that the central here is filled with more dark and bright fringes inside. Then they got more as well. So it's like going through diffraction twice. And also you need to know how different it is if it's different color, because different color light have different wavelength. So you've got over here green laser, yellow laser, and also red laser. So as the wavelength if the wavelength is longer, then the distance between those fringes or between the central maxima to the maximum of the first fringes will be longer too. So that means here red is the longest wavelength and green have shorter wavelength. Okay, so now let's look at diffraction of sound. So firstly is what caused it. So what caused it is always been the same. It's either you have an opening or you have an obstacle. But in the case of sound, we will call it as having a barrier, or of course having an opening. So when we talk about having an opening, it will be something like an open door. So let's say you're blasting music like really loud in a room, and then for the people who is outside of the room, they can still hear the music. But then the sound that comes out from your speaker, if it's a different wavelength, like for example the drum sound, because drum will have like a longer wavelength compared to the sound of clarinet, for example. So the one with the longer wavelength will have a better effect of diffraction. So even if you stand like quite far away from the open door, you can still hear the sound of the bass and also the drum like doom, 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 but you don't really hear the sound of a high-pitched singer, for example. But as you get closer to the door, then you start to hear the one with the higher frequency or the one with high pitch as well. Okay, so that's how it works with an opening. So with barrier, then you can see the example here. So this picture here is more, you will learn this further in university, we call it a Doppler effect. So the sound of the car from the front, okay, when they approaches, they will have a higher frequency or a shorter wavelength. So basically, when the car comes in the beginning, you don't really hear it that much if you got this sound shades for your apartment. But then as it leaves, then you start to hear a little bit of the sound, but at least some of the sound is gone. So that's the reason why you have that sound shade anyway. So that's why if you live in an apartment like nearby the roadside, right? So the sound that you mostly hear is like the end sound of the car leaving, like like that, you know. So that's it. Another example is a marching band. So if you're going through like buildings like this, okay, and then there are people who are playing the drums, and there are people who's playing like violin, for example. The one that plays violin have a shorter wavelength. So if an observer stands here, so he or she will hear the drum, but will probably not hear the violin. In this picture, definitely don't hear it. But as this observer walks over to here, and if he stands here, then he starts to hear the whole band. Okay, so that's the application of the diffraction of sound. Other than that, one that you will learn further later on is electromagnetic spectrum, which is electromagnetic wave. So electromagnetic wave also apply the diffraction of waves as well. So that is how like signal is being transmitted using radio wave, because radio wave has a very long wavelength, so they can diffract off hills, and their signal can be sent without using a satellite. Okay, so yeah, that's basically it for diffraction of light and diffraction of sound. Hope you enjoyed the video. Thank you.